All right, folks, today we're going to start in on Chapter 8. This will be the first video. We should be able to get through a few sections here. We're looking at addition reactions of alkenes. So I'm going to have the slides on the left, and I'm going to scroll through them. Sometimes we will skip things, but I just want to be able to point out things on the slides like I did in class. All right, addition reactions are the opposite of eliminations, right? In eliminations, we were removing two things, an H and a leaving group, and making an alkene. Well, now we're taking an alkene and we're breaking that pi bond and we're adding stuff across it. We're going to be adding halogens. We're going to be adding water and make alcohols. We're going to be adding hydrogens to make alkenes, dihalides, an alcohol and a halogen. It's also known as a halohydrin. And also we will look at some diol reactions. Now, there are some basic steps that we'll see here, but you're going to see over and over again the arrow starting at the double bond and going towards either a proton or an electrophile. Your double bond can act as a base if it's picking up a proton, or as a nucleophile if it's attacking some other electrophile. Klein loves to do this. He introduces a functional group and then tells you why it's important and interesting. And here are some random places where you see alkenes. Alkenes are found in all sorts of compounds. In nature, in pharmaceuticals, in other kinds of industry, and you see just example after example. The petroleum industry can break down petroleum into small alkenes, ethene and propene, commonly known as ethylene and propylene. These are two really important starting materials because alkenes give us a lot of options. We can turn an alkene into many other functional groups. We're going to see, right, we already went through a couple, halides, alcohols. You can also look at epoxides, different carbonyl-containing groups. Often in industry, you're making polymers. So that's just an example of where you might encounter some very basic alkenes in industry. I want to go right into the reactions that we're going to look at, though. In 8.3, you get a little discussion of delta G, enthalpy, entropy. By now, you guys know I'm not going to be asking you about those topics. It does explain sometimes the temperature that you will see when addressing an addition or an elimination reaction. We're not going to worry about that. We're going to go straight into our first reaction. All right, so this is where we really get into the meat of the chapter. We're going to be looking at all sorts, let's see, I want a slightly thicker pen. All right, all sorts of addition reactions. So first we're going to start off with hydrohalogenation because we're adding a hydrogen and a halogen. Hydrohalogenation, X and H. All right, now I explicitly draw this hydrogen because it's the one I added, but it's a bond line structure. I could also have just drawn this, right? Let's not forget our bond line structure rules. Okay, so you can use HCl, HBr, or HI. You are not going to see HF. We're going to note that fluorine can be a little problem child and needs to be dealt with differently. In fact, most of the time you're going to see HCl and HBr. We are going to look at the mechanism of this reaction in a minute, but first we need to talk about regiochemistry. All right, if we add that halogen to ethene, well, it doesn't matter if it goes to the left or the right. They're the same. Whether I draw it this way or this way, these are both one haloethane, right? I've just drawn it a different way. But what about when we have an asymmetric double bond? How do I predict which side it's going to go to? Well, this is part of what you're going to learn here, right? So you're going to find out we organic chemists are quite the control freak. So what we're going to see is that when we have an asymmetric double bond, the bromine goes to the more substituted side. This is known as the Markovnikov product. Right? When HBr goes, what if you want it on the less substituted side? I want to control how to build my molecules, so I might want that product as well. Instead of two bromopropane, maybe I want one bromopropane. Well, you can add peroxides. So ROOR is just a general peroxide. That OO bond is a peroxide functional group. That will change the regiochemistry, right? Which region the bromine adds to. This is known as anti-Markovnikov. There we go. Let's see. You see the same thing here in this example, right? Instead of starting with 1-propene, here we're looking at a 2-methyl-2-butene. And the bromine can go to the more substituted or less substituted place. But you notice we get the product, the Markovnikov product. Bromine going to the more substituted side, the H going to the side where there's more H's. When we look at the mechanism, we'll understand why that is. All right, you add in that peroxide, you wind up getting a different result. Now, they picked a different substrate to start with here, but you notice now the bromine is on the less substituted side, and that is the major product. I am always going to be asking you for the major product. So you're going to have to know if a reaction is Markovnikov or anti-Markovnikov to give me the major product. Now, with the peroxides, you won't learn that mechanism until chapter 10 because it deals with radicals. But we can take a look at the mechanism of Markovnikov hydrohalogenation to understand why we get that regiochemistry. So I'm going to keep using propene over here. I'm just going to come over here. And now we're going to look at the mechanism. Okay? So we're going to start with our double bond and HBr. In this case, our double bond is going to act as a base. And the electrons in our double bond are going to form a new bond to that proton. Now, it's picking up a proton, not the hydrogen. Those electrons stay with the bromine. All right, so just take a minute for me to get the hang of this. We will just bring our mechanism around down here. We will add that hydrogen to the side with more hydrogen because it's going to make the more stable carbocation. Right, there were 2 hydrogens here and 1 here. So the hydrogen, the new one, is going to add to that less substituted side, and that's going to wind up giving us a more stable intermediate. If the hydrogen added to the other side, we'd get a primary carbocation, and that is not as stable. We also generated a bromide ion. That bromide ion is now going to attack, right? Good nucleophile, good electrophile, right? Lots of electron density, less electron density, and that's how our bromine is going to add on. So then, I'll get the hang of this changing colors business. And there is our bromopropane, our 2-bromopropane. It's all driven by the stability of that carbocation. Right, so whatever the more substituted place is, that's where the bromine typically is going to add. We can do just conceptual checks, right? We can answer these problems here. Since there's no peroxides, we are going to be going for the more substituted position. So in this case, there's 1 hydrogen here. There's no hydrogens there. So we're going to put the bromine on that more substituted position. The new hydrogen went to the side with more hydrogen. All right, if we look at this one, it's the same idea, right? Ooh, so messy, I'm sorry. The bromine is going to go to the more substituted position. Right, and there's our answers. All right, so let's just review really quickly, right? Instead of the propene that I started with, right, they're using that 2-methyl-2-butene. It's the same first step. We're picking up the proton. We're breaking the HBr bond. The hydrogen goes to the side that has more hydrogen so that the carbocation can form in that tertiary position. Then you have a great electrophile, a great nucleophile. You're going to get the nucleophilic attack. Something I want to point out is a lot of our mechanisms will have equilibrium arrows. I don't care if you draw equilibrium arrows. You notice on the other side over here, right, I just draw forward arrows. It has to do with all of the, the kinetics and thermodynamics, and is this a reversible step? If I'm asking you for the mechanism to get from start to finish, I'm fine if you just draw arrows that are marching towards the finish. You get a little bit of an energy diagram here. Anytime you have multiple steps, anytime you've got intermediates, instead of just transition states where the bonds are breaking and forming, you're going to get a little dip in your energy diagram, right? Local minima go with intermediates. The proton transfer nucleophilic attack, that's when the bonds are actually forming and breaking up here. Now, the anti-Markovnikov pathway is not possible here, or it does not give you as much. It's definitely a minor product because you get a less stable intermediate. All right, this is going to be the major or preferred mechanistic step because it gives you that tertiary carbocation. Carbocation stability is everything in this reaction. There's just focusing in a little bit more on the energy diagram. You're welcome to take a look at that. Now, because we form a carbocation, right? Remember, carbocations, you saw this. Sorry, I didn't realize that was going to go away. Carbocations are flat. Carbocations can be attacked from either side. So if you had a stereocenter, you would not get necessarily inversion, you would get racemization, right? Meaning that if it was R, you're going to get R and S. You're going to get a mixture because the bromine, or in this case over here, the chlorine, could attack from the front or the back because it's going to be a flat carbocation. And that's just the discussion of a different way to look at the stereochemistry, right? Attacking from the front or the back, the top or the bottom. Now, if there is a carbocation, that means you can get rearrangements. Just like on the last test, I'm not going to ask you to predict rearrangements, but you may have to explain in your mechanism how the rearrangement occurred. Because notice, what I'm saying is I would give you the starting material and the product. And you would see that the chlorine, instead of adding here to the more substituted side of the double bond, it actually adds over here. So you're always going to draw that first step of that base, that double bond picking up the proton. If that doesn't give you the carbocation you need to make the product, that's when you're going to think about rearrangements. Right here we see a hydride shift to go from a secondary to a tertiary alkyl halide. Or I'm sorry, carbocation. Okay, you notice you still get quite a bit of both. That's why I don't want you to worry about predicting rearrangements for me. All right, we'll move on to ask